Welcome back to the Learning Studio. You're watching our mathematics series in the section on data, algorithms, and computation, where we uncover the math that makes AI and modern computing possible. If this is your first time here, don't forget to follow us by clicking the link below, and the full playlist is in the description so you can catch up on all the episodes we've covered so far. Today, we're tackling approximation theory, the mathematics that explains how we can represent complex functions using simpler ones, and why neural networks are so powerful at learning almost anything. Imagine trying to draw a circle using only straight lines. At first, the shape looks rough, but the more lines you add, the closer you get to a perfect circle. That's approximation in action, taking a complicated object and getting as close as possible to it with simpler building blocks. Neural networks do the same thing with functions, approximating reality through layers of simpler transformations. Core concepts explained simply. Here are the essentials. Function approximation. Approximation theory studies how well complex functions can be represented by simpler families of functions, polynomials, trigonometric series, or neural networks. Universal approximation theorem. One of the most famous results states that even a single hidden layer neural network can approximate any continuous function to arbitrary accuracy, given enough neurons. Error bounds. Approximation isn't perfect. There's always a trade-off between accuracy and efficiency. The theory provides tools to measure how close we can get. Practical relevance. From polynomial interpolation to Fourier series, approximation theory shows up everywhere. And in AI, it tells us why deep learning actually works. Why it matters in AI, computing, and technology. Approximation theory is central to modern AI. In neural networks, it explains why layers of simple functions, like ReLUs or sigmoids, can combine to approximate extremely complex patterns. In machine learning, approximation guarantees help us understand model expressivity and generalization. In engineering, approximation methods allow us to solve differential equations, simulate systems, and optimize designs. In science, it bridges the gap between exact models and workable solutions when reality is too complex to describe perfectly. In short, approximation is what makes learning possible for both humans and machines. So, approximation theory gives us the confidence that neural networks can, in theory, represent nearly anything, and in practice, approximate the world well enough to power translation engines, image recognition, and even autonomous vehicles. In our next episode, we'll take the leap into nonlinear optimization, the mathematics behind training deep learning models, reinforcement learning, and the search for solutions in highly complex landscapes. Don't forget to follow us by clicking the link below and check out the full playlist in the description. Each episode is another piece of the puzzle, showing how mathematics builds the intelligence of tomorrow.